All right, so I'll make the introduction, and then we have a few more minutes, and then you both can start. Okay. So welcome everybody to the GCC April seminar. So today is my pleasure to introduce our two speakers, Philipp Niebel and Christina Eichler. So Philipp is a mechanical engineer, graduated at the University of Dresden in Germany, and since 2021 he has been a research fellow at the Technical University of Freiburg. Philipp works on dynamic simulation, modeling, and optimization of crushing circuits in aggregate production, and he has recently completed his PhD supervised by Professor Lieberich. And Christian studied energy process engineering at Claustthal University of Technology, also in Germany. He did his PhD at Hamburg University of Technology, working on the simulation of Howler compaction process using DM, and Christian is currently the managing director of GCC. So today they will share the floor to present the seminar Dynamic Simulation of Aggregates Processing Plants. And so I think Christian is the first one to present. So feel free to start when you're ready, Christian. And thank you for joining both of you. Yeah.
Thank you very much. Yes, I'm Christian. I'm part of GCC, and this presentation is within a collaboration between GCC and the IART, and we are developing in GCC Pro, so our software, new models for crushing and separating. And I'm going to focus today a bit more on the controllers, which we also implemented in GCC Pro within this collaboration. It's a public funded collaboration, so we are happy that this is granted by the German state. Let's start then. I'd like to briefly introduce you into GCC and into our stack. We have two main product streams. The one is a very detailed simulation tool, which is called Musen. It uses discrete element methods to map even single particle collisions and interactions. It's an open source tool. It was developed at the Hamburg Technical University, and we are now proceeding the maintenance of the tool. The benefits of it are that it has a general graphical user interface, and it comes with a GPU acceleration. Thus, you can run simulations on a regular business computer with a gaming graphic card. So, and with that, you can already run millions of particles. So that's the one product stream, and the other side is the process simulator, which is called from DSOL. DSOL stands for Dynamic Simulation of Solids Processes. So it contains already the USP, so dynamic simulations and solid simulations. Especially this combination is unique. And we can describe solids very detailed, so in multi-dimensional distributions if we want, but we can keep it simple and use only particle-size distributions if we are fine with that. It is also, or it comes from research, also from the Hamburg University of Technology, and there is a free version, but there's a free version on GitHub. You can find it on Google or just ask me afterwards. But we just found, or industry told us that the onboarding into the software is way too complex, and therefore we consequently developed DSOL Open further into DSOL Pro, which now has a advanced user interface. The onboarding time is way less, and we have some automation workflows inside that users without coding experience can use this tool. And of course, since we are a company and we'd like to earn money, since both tools are free to use, we have a commercial license on the DSOL Pro version. DSOL Pro comes with 3 key features, I would say. One is the model development kit, which allows the users to develop own models and bring the physics or machine learning trained models into Düssel in either C++ or the new feature is that the user can do that in Python as well, which is very beneficial in terms of machine learning, since most of those models were trained in Python, and you can easily integrate them into Düssel now. Another feature is the calibration tool, where the user provides historical or experimental data, and Düssel tweaks model parameters in that manner to reduce the output of the simulation, or the error between the simulation output and the real data. This is already some sort of optimization, and we can optimize also the other way around. So we can tweak model parameters like design parameters in that case to optimize a user-defined cost function. Like we want to reduce the energy consumption. In the same way, we want to increase the our throughput of one product class. And we have, for instance, constraints that the product quality stays in its boundaries. This can be done by optimizing this process, and we have some analysis tools as well. Okay, but besides those features, we offer also services like reducing the still process simulator environment into a web interface where plant engineers and operators can interact with, and it's predefined. It's a predefined flow sheet which represents the plant, and it contains the ability to change, for instance, the input size or the input mass flow, and track the material behavior within the process over time and in this plant. This exists already, and the next further integration would be that simulations. So there's a backend behind this website, of course, and we can also connect this backend of the Pro directly on a historian, and you can see like soft sensor data straight from the historian database, if you want so. Besides that, we have internally developed a pipeline, I would say, which allows us to rapidly develop and test, and in the end, validate models. So whenever clients come to this point of developing own or integrating own models, sometimes it's costly when they do it on their own, and we can probably do it faster and therefore cheaper for them. And the third point here on this slide, I will mainly focus on are the controllers, which are recently integrated in Düssel Pro, and you can't find it in our test version, which you can download on our website. However, it will be uploaded there soon. So stay tuned, and then you will have these features as well. Controllers in Düssel are, I'm pretty aware that you know already controllers and control theory. However, I'd like to introduce you how we can connect them in Düssel and how we can interact with the flowsheet and which benefits we have there. So, for instance, we can grab information from a unit itself here in a feedback loop over a signal processing unit, which is, for instance, a PID controller or whatever. It manipulates the signal, feeds it into the in this case, a crusher, like a power or a rotational speed. Yeah, by that we can build control loops. We can also grab additional internal variables which are available in these units. Depending on the unit, you can select it. Yes. Of course, we can also have feed-forward loops, thus the signal runs in parallel with the material stream. And one interesting possibility is that we can not only connect to units, we can also connect on inputs. And by that, we can control, so to say, the input mass flow or size or phase fractions, etc. This is probably not 100% process relevant, but you can tweak your flow sheet and you can be very creative in analyzing further, analyzing your flow sheet and your process a little bit deeper. I will come to that point in 2 slides. Besides grabbing information, so grabbing a signal from a unit, we can also plug in a sensor on a stream and grab the stream data, process them, and feed them somewhere else. So that's what I meant by being creative. We have implemented a signal generator where you have just any sort of function which is behind that. And for instance, you can put that on an input mass flow, and you can put noise on it or a signal sine wave function on it. And by that, fluctuations, you can test the robustness of your process, either running multiple simulations or having a long simulation and see how the process interacts with this noise. Yes, and with that, I'd like to show you a brief overview which models we have or which signal processing units we have already implemented. And I have to say, you can connect all these units together and build as complex structures as you want. You can also, so they're fully integrated in the model development kit, so you can integrate your own signals or controllers in C++ or in Python units. And parameters of these controller or manipulating units are also available to be controlled by the optimizer tools which we have. So we can calibrate, for instance, the parameters of controllers when we have experimental or historical data. With that, I'd like to show you a brief example. Here, very simple flow sheet. We have a mill, let's say an impact mill, which we are going to control, or we are going to control the Sauter mean diameter of the output stream in a PID controller, and we control the power of the mill. And what we have in general in the process and in the flow sheet simulations, we are actually having time steps in seconds or minutes. Sometimes we have also milliseconds, but most of the time we have really time frames from seconds to minutes. However, control loops are usually quite fast in milliseconds or once per second. However, we integrated that signals, those high calculation rates or high signal rates. We integrated that in that manner in the flow sheets that it does not affect the speed of Dussel significantly. So it, of course, adds more data and it takes a little bit longer, of course, to simulate these processes. But we found a clever way to reduce the amount of processing time there. And yet now a little example here. You see these Sauter mean diameter in the output stream, and when we set the time delay here, which is probably just a conveyor belt, and the sensor sits at 5 seconds behind the mill, we see we have a nice controlling. And when we increase the time delay, we have some oscillations, and by that we have to redesign the PID values. And this is now something we can do in Dussel directly. So to either optimize the PID values or tweak it manually. or we can think about adding more complexity in this controlling, and or creating a control loop which integrates also this time delay into the control loop. All this is now possible since we can connect everything together. Another example, which is now more to the aggregates, is shown now. Philipp implemented in this project a dump truck, and this dump truck comes with a time-distributed interval. With a time-distributed interval and with a distributed mass, which it delivers every time. And you see that here in this diagram. So it delivers not constantly or in constant steps. And it's fed in a bunker, and then we go on this crusher here. What we see when we look on the bunker runs empty. So, and whenever these runs empty, our stream towards the jaw crusher runs dry, and when the jaw crusher runs dry or runs empty, we have a higher wear in this jaws, and we'd like to avoid this. And therefore, we first analyze how often does the jaw crusher runs empty, and therefore we vary the discharge of the bunker. And we count with this simple signal counter how often is the jaw crusher running empty. And these are the results now. We vary the discharge and see how often the jaw crusher, how many events we have. Since we have a statistical input, and due to our dump truck, we have also error bars in our for each discharge mass flow. Yes, and you see here hundreds of simulations behind that. So the average input of the dump trucks are at around 160 kilograms per second, and when we want to have the maximum throughput through our plant, we have to have a mass or a discharge which is right from this line. Yeah, otherwise we would overload our bunker. And we have a benefit of this jaw crusher. We assume we can control it a little bit in this blue area. So it may be controlled for several mass flows. And this is now something we can benefit from, because we are going to implement a little control loop for this bunker. So depending on the hold up in this bunker, if it's above 50% full, we have the maximum output discharge. If it's below 50%, we set it to a minimum value, which is available or which is suitable for the jaw crusher. And you see an example here. In the green area, you see a slightly larger slope than in the blue area. That means the output mass flow is there higher. And what you also see in this time frame, over 2 hours, the jaw crusher didn't run empty, since the bunker didn't run empty. And what we achieved here is that we reduced from, let's show it here, we come from here about 5 events, events of running empty the jaw crusher to, statistically, it's just once every 5 hours that this event happens. And I think that's a super simple benefit, or a super good benefit for just such a small implementation of a crusher, and for just a small testing scenario. And that's already the part about the controllers And I think I hand over to Philipp. You're muted.
Yes, thank you very much, Christian. I think you should see my slides now.
Yes, go ahead.
Great. Thank you very much. Also, hello to everyone from my side. Now the second part is after we know the basics or the news about Düsseldorf Pro, the second part is about the utilization of Düsseldorf Pro for aggregates processing plant dynamic simulations. And as Christian already said, part of our collaboration is at first that we also create individual models using the Düsseldorf Pro software development kit. And this is what I want to talk about first. And then I will show you some more simulation examples from a processing plant. So here I have an overview about the new individual models we have created here in Freiberg together with Düsseldorf Tech. Some of you already know. Especially my focus lied on crushers, jaw and cone crushers, but I also implemented, for example, a new unit for impact crushers. And so we want it to be a benefit for the utilization of Düsseldorf Pro for everything, not only for aggregates, but also for ores, for rocks, for everything. We have seen the small dump truck unit and the belt conveyor unit and something like a stockpile. This is actually quite easy. It is more or less copy-paste of existing Düsseldorf Pro units and adding some code. And how I already said, I mainly focused on jaw and cone crushers. And this is why I also want to introduce a little bit to the new models at first. And then, how I said at the end, I give you some impressions of entire flowsheet simulations. For the implementation of a new impact crusher model, I've just did a literature research and I've chosen the approach by Nikolov. I adapted it a little bit with knowledge from other literature and also what we teach in our lessons here in Freiberg in our lectures. And so the results look quite good. The models need to be calibrated. Therefore, I would like to remember what Christian said. For example, Düsseldorf Pro has a calibration tool. And if the models are calibrated, as well the PSD itself, but also the qualitative shape of the PSD curves look quite good if you consider the comparison between simulation and experiments. Here in this example, the impact speed was right. So yeah, this is one example for a new crusher type added in Düsseldorf Pro. As next, I want to come to jaw and cone crushers. There, I combined two existing approaches. At the one hand, there was Düsseldorf Pro with its population balance approach, and it works with transformation matrices. And at the other hand, we all know from literature, so I think it's most of you should know, there are for jaw and cone crushers, a typical simulation approach is a multi-stage approach. It takes into account that the crushing or the breakage process is not a single breakage in these crusher types. It is a combination of multiple crushing events or breakage events. So there's a lot of literature, for example, a lot from Chalmers University or also from former EART members. So, and I combined both, so that we now have this multi-stage simulation approach in Düsseldorf Pro. Of course, the particle size distribution and also the throughput can be predicted. And from my side, then I added some more. I thought quite intensively about the residence time of the material in the crusher, considering is it an important aspect of crushing and screening circuit simulation. And I also developed some equations to predict the force distribution in the crushing chamber. Later I will show you an example. Here you can see the setup of the new jar and cone crusher model. Here, for example, of a jar crusher. It's very typical and nothing too much new. There is a transport model or transport function dividing the crushing chamber into the crushing stages. And then within each crushing stage, there is this algorithm. Everything was chosen from literature, but I felt free to mix it a little bit how I consider it fitting perfect to aggregate plants. And so I've chosen the setup in each crushing stage by Silbermann. So at first there is a selection function consisting of stress and breakage probability. After that there is a breakage function, and it is bypassed by the material stream which was not selected. And at the end there is a classification function. It takes into account that even if the material stream passes the breakage function, there could be particles which are too big to enter the next stage and to move down in the crusher. Yes, this is the principal setup. I already told you that I also thought about the residence time. So I want to talk about this now, how I implemented residence time calculation in the Dissol Pro crusher unit, or jar crusher or cone crusher unit. At first I want to say that for somebody is interested more in the residence time, I don't want to tell too much here because this is the main topic of my IMPC contribution this year. But I want to show you how the jar crusher unit works, which I have written. So I added hold-ups. Hold-up is it's I don't know, it's a well-known word, but in Dissol it's used for the amount of material which is within a unit at like a given point in time. So it has the unit of mass, kilogram for example, and I inserted 2 in the crusher. The first one, it is a build-up hold-up. It takes into account that it's possible that the crusher is overfeeded, and so there's material which is already in the crusher, but it's not crushed. And then there's a second hold-up representing the crushing process itself. And for both hold-ups, I can calculate the components of the residence time. So how long the material stream or the material needs to pass these hold-ups. And if I add this together, it is included as a time delay directly in the crushing unit. I can calculate the residence time. I have a small example. It is more or less symbolic. As you can see here, so again, there are 2 hold-ups, and what you can see in the bright blue line, it is the feed material stream of the crusher. And if this is higher than the maximum capacity of the crusher, my build-up hold-up increases, and this is why the residence time becomes longer. So you can see it here between the time shift between input and output. And so I want to demonstrate that with this method, it's possible to dynamically consider the residence time. As next step, I would like to introduce you to the force distribution calculation in the crushing chamber. For me as a mechanical engineer, it's, to be honest, a little bit my favorite aspect of the modeling. I already explained that I have knowledge about the crushing stages, and then it was not a big deal to implement some equations in Düssel Pro to calculate the force in each crushing stage. And so I have the force distribution here, for instance, for a jar crusher and for a cone crusher. It is physics-based. So this calculation, for example, the compression strength and the filling degree on the crusher. And what you can see is that these curves make sense. In the case of the jar crusher here, you can see that the gray dots, if you feed the crusher with bigger particles, there are already at higher stages. So in the upper parts of the crushing chamber, there are higher forces. And if you have a finer feed, like the white blue squares, the force in the higher or the upper parts of the crusher is lower because the material is compressed in the lower parts. The curve for the cone crusher also makes sense in my opinion. It has a choke point and a choked area above this point, approximately at 0.3 millimeter. And below it, in the calibration zone, the forces decrease. What I think what it could be useful for is the combination with between the forces and the wear. So in future, I think it could be possible to include the consideration of wear influence. So how wear, after a long period of time, influences the crushing tool geometry, for example, and how this influences the PSD and the throughput or anything. And also it could be used to derive force assumptions for assembly or component dimensioning. The problem is that this calculation is hard to verify or to validate. During the winter, I made a first try of this because at luck we have a small lab scale jar crusher in our test field. And a colleague, for another reason, he installed 4 sensors, as you can see in the sketch on the right. So 2 in the upper part, at the top of the crushing chamber, and 2 at the bottom. And so I cannot measure the force distribution and compare it with simulations, but I can measure the amount of the resulting force. And I can also measure the point of force application. And this is better than nothing. So this is what I did. And the results show that here in the left diagram, you can see the force vectors and the positions in the crusher. And by calibration of model parameters, here it is the model parameters I've chosen for calibration is KS, the selection parameter, shifts the point of force application upper or lower. And so I can use it to calibrate the model based on another target value. So I have something more like PSD or throughput or anything. The parameter KS is the selection parameter, and it also makes sense. If it is lower, the probability that the particle is selected for a breakage is higher, and so we have a higher force and a bigger force because the particles are selected for breakage in upper parts of the crusher. Here's the wear plate of the jar crusher. It's the old one, but you can see that the qualitative comparison between this force distribution curve and the how the wear looks is also looks similar. And at the right, I just plotted the PSD to show you that it makes sense to use multiple target values. So here on top also is the force to validate the model. I also added the factors why it is not so easy to compare it, because, for example, of the compressive strength, it's fluctuating, and also in Düsseldorf Pro and experiments, I compare a steady state process with actually single particle breakage in our lab scale crusher. Okay, so far so good. Now I will change to the second part of my second part, to the simulation examples. What you can see here is an entire flow sheet of a plant for aggregates or gravel production. It is near Freiberg. We have there were many collaboration together with them during the last decade. It is not important to see in detail. I just want to demonstrate with this big flow sheet that the quite nice new GUI of Düsseldorf Pro is suitable to model many units and also many streams, so big flow sheets. Maybe this is not the biggest, but you see there are, I think at the end it have been approximately around 90 units. You can see some sections. The feed section you have already seen at Christian's presentation. So, for example, the new unit of truck and the primary crusher, he talked about it. But also in the white section, you can see that it's a typical row of silos with different fractions or aggregates with different sizes. And here, multi-deck screen. And it's also possible to implement or to model switches which switch the material stream, for example, towards a recycle loop, back to a crusher, or to truck loading. This is also what the first simulation example is about. This is a simulation of the entire flow sheet. Please do not think about too much about the values of the mass streams and masses itself. I just want to demonstrate that it works very well to simulate with Düsseldorf Pro the entire flow sheet over a long period of time. Maybe, okay, it's not the longest time, but in this case, we talk about 2 hours. Again, you can see the truck feed of the plant and the pre-bunker. And at the bottom, you can see that these switches I talked about, sometimes opened, and different products are loaded to trucks. And the corresponding silo masses. So this is what you can do, and of course, also because there are the models behind all of these units, it's not only about mass streams, it's also about the particle size distribution. You can see all of the particle size distributions in the silos, which are loaded to trucks or everything. And this is at one point in time. Of course, it is dynamically, you can see the changes. And all of this is at the moment without the control structures Christian introduced you to. So if you combine this, there are a lot of possibilities to optimize controllers, machines, processes, everything you can imagine. My second simulation example is about in this plant. So it's a section of the flow sheet. It's about the secondary crushing circuit. You can see that it is a cone crusher in this case. And in this crushing circuit, there is a screen and also a silo, but I neglected them for the simulation just to show you how the ramp up can be investigated in Düsseldorf Pro. So the feed starts from 0, and then you can simulate how long it takes until you reach a steady state point in the plant. Again, you can see the time shift between the mass flows, which is the residence time of the crusher, and also on these belt conveyors here. If we click through the timeline, watch to the right to the PSD diagram, you can see that you can see how it changes dynamically. And at the end, we have a steady state particle size distribution. So then I will come to my third example. You already know from Christian this section of the flowsheet. It's with a dump truck. It's a feed section of the flowsheet with a primary jaw crusher. So here, but I don't want to talk about control structures. But remember my jaw crusher unit consisting of 2 hold-ups. I want to demonstrate how this could be useful. It's very common that from the trucks that the feed particle size distribution fluctuates, and if it's a case, for example, that the feed material becomes coarser, then the coarse fraction of the pre-screen produces a higher mass flow. So it's the bright blue line. And here, in this case, if the feed material is too coarse, it leads to an overfilling of the crusher, because then the maximum capacity of the crusher is lower. And you can see that the hold-ups I showed you before and also the residence time increase. Then if the feed material becomes finer, now it's finer. Here it is coarser. You can see it in the white in the particle size distribution diagram. Now it becomes finer, so the build-up, hold-up decreases, and so on. With this example, I want to demonstrate that the units or Düssel Pro can be used, for example, for dimensioning of the crusher itself, or of the chutes above the crusher, or to dimension the pre-bunker. And also, and that's now closing the loop to Christian, consider or imagine we add or we use the data of a filling degree sensor, which is common in jaw crushers. We could use it to optimize the control structure or the control loops with Düssel Pro. So I will come to an end now. I would like to sum up. From my side, in the collaboration with Düsseltech, it is about making Düssel Pro much better for work, for ore, for aggregate processing plants, and we implemented new models with a special focus on crushers. And yes, this is what we did. At this point, I want to add that, of course, the model validation and the verification and the optimization is an ongoing process. We still make some trials, or if we get some data from some plants, we try to simulate it. My personal extended focus lies on the residence time and the force distribution. But at the moment, we can say that our collaboration, our project, our funded project already enhanced the capability of Düssel Pro for dynamic flowsheet simulations of rocks, ores, and aggregates and the processing plants. So thank you very much. Feel free to ask Christian and me all questions you want, and thank you.
Thank you, Philip and Christian, for the very nice presentations. So we're open for some discussions. If you have it, just open the mic and speak up.
Maybe to keep with my reputation, I'll start up at Malcolm Powell. So really enjoyed that, Christian and Philip, and been involved with trying to get us more involved with Düssel for some time, as you know, and really good to see a lot of what we wanting to put into the GCC version, you're already building with to see your convergence routines and optimization routines. Really nice. So to ask a direct question for Philip, that's a circuit with 90 units in it and some recycle and so on. When you simulate it, how does it compare to how fast can you simulate relative to real time?
Yes.
It always depends on the models. Sorry, Philip run the simulations, but Philip, continue.
Yeah.
Sorry, no, I will switch back to the slide. The simulation ones on my standard Office PC are faster than the simulated time, but it still took a while. I think here I simulated 2 hours with this approximately 90 unit flow sheet, and it took, I think, about 75 minutes or so. So it is faster than reality. Yes. The question is if it need to be faster than reality. Yes.
Yeah, it depends on the models. When dynamic simulations is always looping over looping, and it takes a while for us. However, we can speed up units, and so building surrogate models, just build data models. This is commonly used by us, and this, to be honest, is a very huge flow sheet, and I think one of the largest ever simulated in Düsseldorf Pro. So usually we have smaller flow sheets. So depending on the scope, of course, we can accelerate it. When it comes then to real time optimization, probably we have to be, I don't know, 100 times faster than real time. But yeah, depending on the task, we can work towards that. But yeah, sometimes it takes a while when we want to have this full resolution simulations.
But still, it's a huge circuit. It's impressive. You just working, on your laptop, first pass, and you're already faster than real time. Don't apologize for it. It's good. So I'm impressed with that, and that's you're getting a design tool that is the same tool that you could actually end up using in optimization and control. You'll easily get this to 1/10 of the simulation time just by architecture. So it's actually really impressive. Well done.
Yes, sometimes there are some issues. For example, if you set some mass flows or PSDs not in the correct way, then an error may occur. But if everything is correct, it runs.
Marcelo has a question.
Yes. Well, the same way as Malcolm, I'm really impressed. Very nice to see some fantastic developments in the Düsseldorf Pro, and indeed, nice to see really the control capabilities that really came through this year. So we're really looking forward to really have this GCC Düsseldorf Pro version out and to really engage more the sponsors into this proposed project. So we need to really push that forward during this year. But so really nice to see that things are evolving. And I think indeed a crushing circuit is a particularly challenging one for dynamics, because there's the obvious dynamics in the circuit related to the conveyor belts, but it's nice to see that Philip went beyond that, which is looked at inside each operating unit, which is like individual jaw and cone crushers. And there's definitely value in the short-term dynamics. So really great job there. My questions to Philip are just 2 quick ones. The first one is that, of course, you mentioned about force distribution and so on. But of course, I know crusher operator is actually looking at power at the same time. So I was wondering how well the power models are actually behaving in these crushing units, because in the end of the day, that's most often the variable that is people use to control operation. And the second quick question is, yes, very nice, the dump truck simulations there, because that's an important dynamics that comes from the mine and actually interacts with the plant. But I was wondering about the size distribution type of variability that we see, that really introduces one source of variability that is very kind of hard to really map, because we don't measure that in the truck. But if you have any feeling on the impact of that variability in the run of mine size distribution on the predictions, when you actually compare, at least qualitatively, with real life, the fluctuations that you see in the simulation in comparison to the plant. That's really great job.
Yes, thank you very much. Maybe at first to the power. I know this is what I said. I'm a mechanical engineer, and so I'm also interested in a component and machine and assembly dimensioning. But of course, this approach can be used also to predict the power, and it could be compared then to the power. So origin where I got this method from, or from the literature, is also, or usually in our lectures we use the force in the crusher to calculate the power. So yes, and for the dump truck particle size distribution, all of the simulation examples were or are more or less symbolic or fictional. So I know that we have no data, but you are right. Yes, it could be possible if we make, I don't know, many simulations, and then we can investigate the impact of the fluctuate in PSD. So the PSD I changed for the simulation is just an example with fictional values.
Thank you.
So, Benoit.
That's it. Thank you, Benoit from Makoto. Thank you again for the presentation. I have just a quick question. When you mentioned that you focus on force distribution crushing chamber, the example that you show was more on the compression, meaning, you know, the jaw crusher and the cone crusher. And I would like to know where are you, what is the status regarding impact crusher, such as HSI or others. So could you extend a little bit, or? Thank you.
The force distribution calculated are also I only implemented for jaw cone crushers. So for impact crusher, it's just implemented the model from literature, adapted a little bit, but without forces or any wear aspects.
Okay, thank you.
Any further questions from the audience? We still have a few minutes. Oh, yeah. If we don't have further questions, so let's thank you again, Philipp and Christian, for the very nice presentations. And thank you all for attending. So this recording will be available on the YouTube channel. And next month we have another seminar. You will receive the invite in the meantime. So thank you very much, and see you next month.
Thank you, everyone.
Thank you.
Thank you. Bye-bye.
Bye-bye.
Great job, thanks.